But antiderivative and antidifferentiation, you understand what those are, right? So this was a notation. Stretch S symbol, f of x. What is the antiderivative of this one? And this notation does not represent one antiderivative. It represents collection of all antiderivatives. And I was also being careful in that we usually don't consider this antiderivative in the big range. We usually consider antiderivative over one single interval. And there's no notation in here that indicates, which interval we're talking about. So this notation is convenient, and you have to understand this context in that problem that you are working on. So when we're just writing things like this, we don't specify which interval we're working on. So this notation makes sense? Antiderivative versus the antiderivatives, plural form, right? These are the all antiderivatives. And what's the name of this one, this whole symbol? Indefinite integral, right? The indefinite integral of f of x is the set of all antiderivatives. And we looked at this example that it seems like all the functions that have derivative 0 must be constant, right? That's our intuitive thinking. And then we had this weird example, doesn't look like constant, but it was a constant, makes you think about maybe we have to approach this one a little bit more carefully. It's usually so here's a theorem of antiderivative form. So they formulate it as a theorem. That's not trivial. We have to think about this one carefully. That's what this is about. And I think it is stated here, antiderivative forms. It is pretty much a uniqueness theorem. Uniqueness means there's only one thing, right? How many antiderivatives are there? Infinitely many, by adding the constants, right? But they're not totally different. They're very, very similar to each other. So it is a kind of unique in its form. So if you have two functions whose derivatives is the same, so antiderivative of same function, right? These two are an antiderivative of the same function. And over one interval, then they must be related like this. G of x, the other antiderivative must be constant term plus the one antiderivative there. Okay? I think because of that, the meaning of the symbol is a set of all antiderivatives, right? That was very meaning. And this theorem allows you to state that because of that theorem, this antiderivatives is f of x, one thing you found, plus c all the time. No matter who found it, it is just a difference of a constant. So this is not a definition, right? This is a theorem. What is the definition of the symbol? Set of all antiderivative. Thinking about the conceptual antiderivative, no problem. So that's how it's defined. Now it is being written like this. That's a theorem. Do you understand the difference between definition and theorem here? Yeah.
So the other one was a definition?
Right. The definition was this one in here. This one was a definition. What is the symbol representing? The set of all antiderivatives. And it is a mathematical theorem that they all look like that, f of x plus c, right? If you find one, and all the other thing looks like that. All right, so let me explain why this theorem is true. Okay. When we explain things mathematically, it means logically and not relying on pictures and intuition, right? That's how it's done. So let's look at this equation, g of x, and manipulate it like this, right? Which is equivalent. If you can prove this one, then you're proving that one. And left-hand side looks like a function, and right-hand side is a constant. So it motivates us to define one function, h of x, being g of x minus f of x. It's not solution, it's called proof. Mathematically explaining why this is always the case. So we have that, and then wait a second. All right. So now we want to show that h of x is a constant function, right? And then notice that derivative of hx is derivative of g of x minus f of x, right? And this derivative operator is called the linear operator. Linear operator means if there's a constant multiple, you can go outside and in freely, right? If there's addition and subtraction, this linear operator can be distributed, right? Did you have a question? So it's actually one antiderivative. The key term is that it's a one antiderivative, but it can represent any antiderivative. So we call it arbitrary antiderivatives, right? It's a good point. Those quantifiers is actually key things to understand many of the mathematical arguments. So here, this one distributes over, right? So it can go there, and it can go there, right? What is this property called? Linearity, right? If you see this nonlinear and linear phenomena a lot in many literature, it's exactly talking about this phenomenon, right? All right. Then what is derivative of g of x? F of x? Because f of x and g of x is antiderivative of little f of x, right? So what are the derivative of these two functions? F of x minus f of x. So what is it? 0. So we're staring at a function whose derivative is 0 on that interval a to b, right? So we kind of reduce it down to that simple problem. We're looking at some function we don't know, but we know its derivative is absolutely flat 0. Can we conclude that h of x is a constant function? And that seems like intuitively is true, but we're explaining it here, right? So we want to show h of x is a constant function, right? So we've seen this a lot. Suppose h of x is not constant. Not a constant function. Then you use this hypothetical situation. You use logically, it must follow this, and then later at the end you realize, oh, 0 equals 1. Then what's the conclusion? Whatever you have supposed here is necessarily wrong. Therefore, it must be constant, right? So what does it mean is the function being not constant? There are two values, two numbers. I'm going to call alpha and beta, and I already use a and b. So alpha and beta, sorry about that. Alpha small and beta larger, such that h of alpha is not equal to h of beta, right? If it is not constant, there must be two values such that the value is different. If it's constant, whatever two value you choose, it's going to be always the function value is the same. And alpha and beta are in that interval. Everything is happening inside that interval, a to b. Correct? All right. So how can we break this one down? H of alpha minus h of beta different. So this part from here was actually specified in an advanced problem. So here's a case. What if h alpha is smaller than h beta, right? If it is different, one thing must be greater than the other, right? The other case would be h beta being smaller than h alpha, right? If it is different, either of the two cases must be true. Have you seen, we've done this a lot, inequalities, and suppose that's not true. And what was the main tool that we use over and over? What theorem? Mean value theorem, right? So mean value theorem on that interval a to b, alpha to beta is what we're gonna do, all right? So anybody remember mean value theorem? Right. So there is this slope of a secant line, right? So what is it in the denominator? Right, beta minus alpha. Exactly, that's the interval. What's the numerator? H of this, we're applying this mean value theorem and on that interval and the function h of x, right? So it's h of beta minus h of alpha, correct? Supposed to be equal to h prime of, let's say, c. And where is the c? strictly in between alpha and beta. Is that right? That's the conclusion of mean value theorem. If these two things doesn't matter, is less than or equal, if there's this interval and it's differentiable function hx, then this must be true, right? Let's use this condition to see what this left-hand side implies. We only know something is greater than something, so it's probably the sign, positive or negative part. Left-hand side is that positive number hp minus h alpha? It's a positive number, right? So it's a positive number divided by beta minus alpha is not 0, it's a positive number. So together must be a positive number, which must be the right-hand side, h prime of c, right? Okay, so that's the conclusion from mean value theorem from that hypothesis, right? But the only fact we know about this h of x, what is it? The only information we know about h of x is over there. What do we know about h of x? G of x minus f of x. But what about that h prime of x? What do we know about h prime of x? What's equal to 0? Flat 0. Whatever you plug in, you must have 0. That's what the h prime of x is 0, right? So, on the other hand, h prime of x is 0 for what kind of x? All the values x in that interval a to b, right? All right, that's from given fact, and this is our hypothetical situation, and we got the conclusion that h prime of c is what kind of number? Positive number. So, do you see what to write in the next line? This is absurd. Yeah, that's the word. And it's absurd. Going back. So, what is it? H of x must be constant function, right? But I didn't cover the other case. Maybe h beta is less than h alpha, right? You see the only thing that changes is the negative divided by positive. So still giving you non-zero number, so it's a problem, right? So the correct conclusion here at this stage is, if this doesn't happen, what's the other case? H of alpha must be greater than or equal to h of beta, right? Right? But we know h of alpha and h of beta is different, right? So this must be the case. Now you proceed with this case and you pull out another contradiction, right? Absurd again, and then you go back and see what else is out there, and it all happened because we assume there are two values with a different function value. It ends up in a contradiction. So there isn't any two value at a different function value. Every two value you choose, they're always the same. That's a proof of it's a constant function. All right. So mean value turns out it's a pretty nice tool to argue cleanly in here and take care of this case right here. All right? You see what's going to happen? This is going to be a homework, right? Yeah. Doing the other case and wrapping up. All right. So now we know why, if you have one antiderivative, all the other antiderivative must be in that form. Okay? It's because, let me show you and then I'll take your question. Because h of x is a constant, so here you put, now we know h of x is a constant. If it is not constant, it's a problem. Run into problems. So you put c in there, then you go back in here and prove in all that. Question, Laura. All right, now we accept that, and it was important because this is this conclusion, it's a unique solution there, is applied to differential equation problem. That's how all the physics problem is formulated, pretty much. All right, so we understand this thing as a theorem, not definition, right? What was the definition of the symbol? All antiderivative. Thank you. And we did all that problems. Let's see if I have one more thing to say. before we go into that. We explained that. I already phrased that, showed you in that slide. Oh, before we go on to the next part, just clarify of this term. Antiderivative is a function, right? Antidifferentiation is an action. Your process of finding an antiderivative. An indefinite integral is the collection of all antiderivatives, right, which are functions. And in my course, I will say integrate this, integrate that. That means you antidifferentiate that function or compute all the antiderivatives. Fair enough? Otherwise, I'll be more specific. Compute the integral, compute the indefinite integral, compute the definite integrals. But when you say integrate, this mouthful word, I don't want to speak all the time, antidifferentiate, so integrate will replace that. Any question about the terms? Good mathematical understanding starts from clear understanding about the definition and absorbing all the conditioning behind it. Right? If you try to simplify mathematics, you increase the room for mistakes and misunderstanding. All right, basic integration fact. And there was a homework problem, so let me challenge you with some of the facts, right? Exercise number 1 today. That if you did that homework, always remind, oh, he seems like want us to memorize this, not just copying it down in the homework, right? So let's start with this. X to the n, antiderivative x to the n. All right? It has 3 parts, each of them 1 point. Give yourself, I think it had more, so each of them give yourself 1 point. So it could be more than 2 points, maybe 6 points or something, this exercise. So what is the antiderivative of x to the n? X to the n. Right, correct answer? Somebody like to go for it? Think about the power. It must have come from which power? N plus 1. It must have come from n plus 1. However, this is not it, right? We have to adjust the constant multiple. What was it? 1 over n plus 1, right? But this is not the full answer. There's a condition. This only makes sense if... No? N, about is n. N cannot be negative 1. And cannot be negative. You wonder then what happens when n equals negative 1, right? Okay. Let's just take care of that now. Yes?
Does it matter if that 1 over n plus 1 is behind that x n plus 1?
No, it doesn't matter. Yeah. But... No, it doesn't matter. That's it. All right. This n this n here is not really integers. It can be real numbers. So you can keep your answer in that way, but I'm going to change this number and change the letter to alpha, and many mathematicians will think, oh, maybe that's suggesting real number, all real number, not just 1 and 2. It could be 1/3, it could be 1 whatever, that you can use this formula all the time, right? It's so basic formula. For some reason, student, whenever this becomes 1/3 and fractional exponent, student don't know what to do. This is it. No matter what that exponent is, you apply this rule, not just for x to the second, x to the third. Okay? So give yourself 1 point if you got this one right. What is the second problem then? X to the negative 1, right? What's going to happen to x to the negative 1? So which is also denoted by 1 over x, right? All right. For the second point. All right, who remembers the answer? ln of absolute value of x. Strange, the absolute value of x, right? And then I forgot to put c in there. That's not good. You have to clearly, go by the definition. These are collection of antiderivatives. The reason there's absolute value is that ln x has, what is the domain of ln x? Only positive numbers are allowed, right? You can't put negative number in there. Left-hand side, it can be negative. X can be negative 5 here, right? So if you write down ln x, that will be only meaningful for 0 to infinity, right? So if x is in the negative side, what could be the answer? And you can just play with, okay, 1 over negative x. That puts this one into positive, right? then you can use this thing, and it turns out this notation sums up all. And this function is divided around x equals 0, is not defined at x equals 0. So this is the answer. And when you're computing so-called definite integral, remembering this formula of ln x correctly in that, like that, is important. All right? So make sure you keep that absolute value of x in there. Okay, so that takes care of this basic case. And what are the next kind? Trigonometry, right? Let's go for trigonometry. So what is a sine x dx? Let's go for two of them together. What is a cosine x dx? So that's kind of a side by side. So altogether, this is 1 point. You shouldn't give yourself partial credit because you have plus c part right. You have to get the other part correct. Alright? Always check. You differentiate your answer. You're supposed to have that integrand function. The function inside here, integrand function. You have to have that one back. Any question? So the third one, it actually appears used a lot in calculus 2, is secant square x. Correct answer? Not that. Tangent x plus c. Alright? So you basically go through the derivative table and write it backwards, right? So what is the third one that is natural from the derivative table? Is next one is a secant x times tangent x. Yeah. So don't look at this one. Just go through the derivative table until you bump into this guy. Right? Correct answer? Secant square x. Right. These I require for you to memorize the derivative of these functions. So backward. And knowing this much, it's sufficient to attack all the problems in the Calc 2. So this is what I require. Okay? Which one? Not the other one, not tangent, and we will actually calculate that, but this is required to memorize it, right? All the things we'll use substitution method and calculate it eventually. All right, this is the minimum is required for trigonometry. The next level is exponential, right? All right, let's try. Easy one, e to the x and dx. I want you to do that. And together with this hard one, 2 to the x dx. Just remember that. So all together, give yourself 1 point. So who knows the answers to the second one? Right. 2 to the x is there. You know if you differentiate this one, you have this one back. But there's multiplicative factor comes out. That was ln2. So you have to kill that ln2. If you differentiate e2 to the x, 2 to the x times ln2, then they cancel, becomes 2 to the x. Nothing special about 2. You can be 3, whatever, right? But I wanted to use a number so that you clearly understand the formula. Book has a to the x. Look at that formula. All right. That's pretty much it. Right? We did already ln x. Okay. So these are the basic derivative facts you're required to memorize. Especially pay attention to this one. Students usually pay attention to that one and forget about this alpha can be anything. Right? Yes? We'll go through loads of antiderivative problems that will cover pretty much everything you can imagine. Alright. So they're there. It's alright. Then at the beginning there they listed the rules. So here is a summary of the rules. Those are the facts and here are the rules. They're like derivative rules, right? This derivative operator, the integral symbol, is actually a linear operator. The meaning of linear operator, constant multiple go in and out, right? And it can go inside over the addition and subtraction. Okay? So, for example, let's see what I have in there. Oh, and I'm also emphasizing it here. It does not commute with multiplication and division. Remember, if you have derivative symbol like this, d dx of x times x squared, then you think about, okay, I'm going to differentiate. Many of you did this one in the test problem, right? When you were asked to compute use the second derivative test, many of you differentiated this function like that. This is what I mean by commuting with multiplication. This operator does not distribute over multiplication. This is x to the third, right? So what is the answer to that one? X to the third, 3x squared. But what is the derivative of x? 1. What is the derivative of x squared? 2x, right? If you multiply, you don't get 3x squared. So they're not equal to each other. You can distribute this operator over multiplication and division. And there is a product rule, how to do it. So the same thing, you cannot distribute this integral symbol over multiplication and division, and there is integration by parts, substitution rule to handle that kind of complicated case. But over addition and subtraction, it's not a problem. So for example, if I ask you to compute, as an example, of sine of x plus 3 to the x dx, what is the antiderivative of this function? Then you can do, because this is a linear operator, right? You can distribute that over like the sine x plus 3 to the x. You know, this symbol distributed as if it is a number multiplied to that, right? But this operator symbol has this end placeholder dx, and you have to distribute the dx from the right as well. Is that okay? Yeah. So you can calculate sine x. What is sine x? Antiderivative is negative cosine x, is that right? Plus c, right? Because it's individual. So I'm going to call that c1 because I'm about to have another one there, right? Okay? So how about this one? Who remembers antiderivative of 3 to the x? There is 3 to the x, right? What was the 1 over ln 3? And then this guy is going to have another constant, right? So let's group them together. This is the actual function part. Then there is a constant c1 and c2, right? Put them together. And you realize there's no reason to rewrite a c1 plus c2. You can just all write it as one constant, right? I hope that makes sense. All right, so let's look at the next example that uses constant multiple. E to the x plus 5, we do not have derivative rule for e to the x plus 5, right? But you see that you can do some little algebra to rewrite this expression. It looks different. It's called exponential law. How is that separated? E to the x times e to the 5, right? Now it looks like e to the 5 is constant, right? And it's a multiple. And what do we do with a constant multiple? You can put outside integral, commute with that. So this guy go outside, and you're left with something we know, e to the x, right? So what is it? E to the x, right? And plus c inside. Let's write down c1 again, because you realize that, oh, if you distribute, you get a simpler form. Any questions so far? Then you expand it. Oh, that's e to the 5 times e to the x plus e to the 5 times the c1, right? c1 constant, e to the 5th constant. Everything is constant, right? So we can write this one as just a c, correct? And how about here? That was the same thing as before, just a times b and b times a. So you can rewrite it back, e to the x to the plus 5 plus this whole thing called just a c. So this is probably the answer you're going to see in the back of the book. So what are these two things called? Property that I just used? Linearity, right? You can pull out constant multiple. If the addition and subtraction, you can distribute the symbol. All right? It's because differential operator was a linearity. That's pretty much what it is. So here's your exercise. Well, I thought 23 is fun one to do. So, yeah, why don't we do 22? What was that? Exercise previous 1 plus 1, yes. All right. Use your incredible logical skill, right? Don't use your intuition. Okay? All right, how was that? Okay. First, you realize that no immediate rule is applied here. I don't see any constant multiple right away. And because of the square, I don't see this as a sum of two things, right? It's rather a product of two things at this stage. So I wrote it here. No, the linearity rule is immediately applied here. So I changed the expression. 2t plus 3, 2t plus 3, and multiply them out. Now it's a constant multiple. I know how to integrate that. I know how to do that. It's all constant multiple. So first you distribute the symbol over the addition. So we have, 3 integrals added together. And then you can pull out each of the constant multiple out, and the inside becomes more of a trivial basic facts integrals. It's like that, and it's invisible 1. So that becomes this one plus c1. This one is a t to the first, so you bump up t squared, always there. So pretty much when you integrate this basic part, this exponent up here in the denominator, here, this is how I remember this one. The third appears exactly down there. Second appears exactly down there, right? Or another better way is a reciprocal appears. So think about t to the 1/3, how it's gonna go. If you add 1 there, what do you see? 4/3, right? 4/3 there. If you add 1 to the exponent, it's 4/3, right? What's in front of it? Reciprocal. 3/4. Right? So that's a convenient way to remember how this thing works. Exponent and reciprocal out there. Okay? So that's all that is. Reciprocal here is 1, so I don't do anything. Now you collect all the function part, and the constant part looked like this, and you realize, oh, whatever the c1, c2, they're all together constants anyway, right? So you put in that simplified form. So this is the indefinite integrals, and that first 3 terms together is 1 antiderivatives, and all the antiderivative is described in that form, and that was a theorem. Fair enough? All right. I'm just stopping here. So that was that fact, an example we went through. Initial